Fantastic. I think we are going to get started. So, good morning, everyone. Happy Monday. My name is Harriet Bredel. I'm the Exec Director here at the Keck Institute for Space Studies. It is such a pleasure to see you all here today for our short course on, I have memorized it, don't worry, but One Shot to Glory, Designing Adaptive Missions to the Outer Solar System and Beyond. We have a fantastic lineup of speakers that we're going to learn from today. So I'm going to talk very little. Before we get going, I just want to introduce you a little bit to the Keck Institute, which is based here on campus. And to do that, I want to share a very quick video that tells you a little bit more about what we do and what you can expect from our institute. So,
the Keck Institute for Space Studies is Caltech's Think Do tank for space exploration. We look at advanced out there concepts for how to observe the Earth, how to gaze into the heavens beyond, and then what are the technologies that enable us to explore and create the data sets of the future. KISS's mission is to revolutionize space studies. We seek far out concepts that have breakthrough potential and seed the teams and investigators behind those concepts.
It's a really passionate group of experts that we're bringing together who really see a positive, expansive future.
I think what makes KISS unique is the level of ambition of the ideas that are being discussed.
It takes crazy ideas and it funnels them and channels them into something that is actionable and yet truly futuristic.
That kind of far out thinking lays the ground for audacious missions of the future and audacious technologies, and that's what KISS seeks to enable, is to make what is presently impossible possible.
all right. Thank you. So I have to say that this study that brings us all together, I think, really embodies that spirit. We are here to think bold, come up with creative, maybe crazy ideas of what space missions and space exploration can look like in the future. So to do that, before we get started, I want to give a fantastic thank you to our 4 study leads of this program. So if I can ask Hiro, Morgan, Danny, and Sinjo just to quickly stand up, wave, say hello. Perfect timing. A round of applause for them as well. We would not be here without them, and they have been orchestrating this fantastic short course and the week ahead for those of you who are joining us for the full study program. So with that, I am going to get started by handing over to Hiro Ono, who is going to give us a little bit more of an introduction of what is bringing us all here. So Hiro, over to you.
All right. Hi, everyone. Good morning. Happy Monday. Go Dodgers. I'm Hiro Ono. I am a roboticist at JPL. I am one of the study leads. So what I do, as Harriet said, there are gonna be five speakers. I'm gonna do a little introduction to put them in context. Okay, so let's dive in. How to advance this slide? Let's see. Hello. There you go. Okay. All right. Sorry. So. Just one slide summary of everything that you're going to hear today. The current robotic space exploration paradigm, which for convenience I call RC 2.0, is like a panda on a busy street. And the workshop is to create a new paradigm, RC 3.0, that is a little like a rat on a backpack trip. Okay? That's all you have to learn. Well, it's not all, but anyways, what does it mean? You will learn it by the end of my talk. All right, so let's start from this question. Why do we explore space? Why? Why not? Yes, because there's space, right? Yeah, because it's there. All right, so this is what I would put it. Because we know so little about it, right? We are ignorant. There are two implications out of our ignorance. For science, there are just still so many discoveries waiting for us to discover, right? And that's what Morgan Cable is going to talk about right after me. And I won't spoil her talk, but just one slide, something that I'm really curious about. For example, right? If you go out there in solar system, there are so many moons, ball of ice, right? There are many moons made of ice with subsurface oceans. For example, this moon Enceladus, that's 3 times bigger than this star, has subsurface ocean and geysers, and scientists like Morgan and Amanda maybe are speculating that there could be life. Is there life over there, right? So that's one of many discoveries to be there. All right, so the other implications of our ignorance for engineering is that there must be so many surprises to be encountered, right? Because looking back, the space exploration has been full of surprises. Bad things could happen, right? Pointy rocks on Mars, what happened on Curiosity, you see those gigantic holes on the wheel, right? Or when Osiris-Rex flew to asteroid Bennu, surprise, surprise, the surface was super rocky and the landing and sampling was challenging. When Perseverance tried to take the first core sample, the rock turned out to be surprisingly soft and it crumbled to pieces. I've been on Perseverance Ops since like 2021, landing. It's full of surprises. Every day, it's small surprises, big surprises. Driving on Mars never be like a highway trip. It's more like adventure. So, so that's the two major implications. We are ignorant. All right. So what remains to be explored? Well, obviously there are a lot, right? So here's one slide summary about the current status of solar system exploration. The numbers on the table shows the number of missions. And on the horizontal axis are the major targets in the solar system, from Mercury, Venus, Moon, all the way to Pluto and Centaurus, KBOs. On the vertical axis, it's the mission types, right? From flyby and orbit to atmospheric, surface, subsurface, and sample return. We've been doing pretty good job on flybys, right? We flew spacecrafts to all the 8 planets and many of their moons, small bodies, but flybys are just initial reconnaissance, right? And when it comes to any in situ missions, surface or below, there are only 3 bodies in the solar system which we have done exploration, 10 times or more. Venus, the Moon, and Mars, right? And anything beyond in the solar system is either unexplored or underexplored. So the big question that we are asking in this study is how to enable the missions like that. All right, and a partial answer to that, well, it's not an answer maybe, a requisite to enable such mission would be a fundamentally new exploration paradigm. For the convenience of argument, I categorize mission into 3 regimes. RC 1.0, that was in the past, 2.0, current, 3.0, in the future. That's something we're gonna create in this workshop. 1.0, what was that? That was basically the lunar exploration before Apollo. Right? Between 1958 to 68, NASA and JPL sent 20 missions to the moon, and only 8 were successful. So this 1.0 paradigm, that was basically fast-paced trial and error. That's basically the things that commercial companies are doing these days. There's nothing wrong about it. Probably this is the best way for the moon, actually. Because, moon is just 3 days away, right? And launch opportunities comes up every month. So we can do try and error every month to quickly learn. And it actually went well, right? But this try and error doesn't work for Mars. Why? Or simply because it's too far, right? It takes 6 to 8 months to get there. Launch opportunity is only once in every 26 months, so you can't just try and error every month, right? So what we did in the past 3 decades, NASA JPL sent 14 missions to Mars. 11 were successful, right? Great. But this RC 2.0 is not just about being cautious. It's more about being incremental. Every mission, we started from easier one. We learned something. We learned about the environment. And we use that knowledge to upgrade the next mission. And we incrementally made a progress all the way up to, the current Perseverance and sample return. So conceptually, here's how it works, right? Initially, you don't know much about the environment. There's so much uncertainty. So you start with low risk, low complexity missions like flyby and orbiters to bring down the uncertainty a little bit and use that knowledge then to build a little more complex mission to the surface, and maybe some simple rover to learn more about the environment. And once you obtained an intricate knowledge about the environment, now it's time to build a super complex machines like Perseverance or Curiosity to explore in depth. And we were very successful in this way to explore Mars. I'm being so proud to be a part of it. But a question that we have to ask is that, can we just keep doing this? Right? Can we just keep doing this to explore places beyond Mars? Probably no, for 3 reasons. One, the cruise time to the outer solar system is pretty extensive, right? 5 years, 10 years to Jupiter, Saturnian systems. It's not like 3 days to the moon, 6 months to Mars. Second, if you are interested in going to subsurface, orbital reconnaissance doesn't help anyway. And third, I think this is the most important. We've been pretty much focused on Mars in the past few decades, but there are so many interesting places to go, right? So can we send like 10 or 15 missions to each of those interesting places? Yeah, we can if we have a few centuries. We don't want to wait that long, right? We want to see it within a lifetime. So we got to figure out something different, right? We got to figure out that's more direct, that's more get it done more quickly, skipping the steps. So that's the RC 3.0 that we envision. That's one-shot exploration with highly adaptive systems. This is what I imagine is going to work. The beginning is the same. You don't know much about this new place, right? But you send this hyper-adaptive system into this unknown, but start with low-risk, low-complexity behaviors, maybe just looking around to observe the environment, to gain some knowledge, reduce uncertainty. Using that knowledge, the same system will adapt its behaviors to, perform a little more complex tasks like moving on the surface to gain more knowledge and reduce uncertainty. And finally, it adapts again to perform more complex behaviors, maybe diving into subsurface. So RC 2.0 is a little like Panda, right? Panda, cute but poor animals, like after the invasion of Homo sapiens, right? Their habitat is basically confined to very small regions in Chinese mountains, Why? Because they can only eat bamboos. They're very picky. They can only live in bamboo forest in higher elevations. So they are not very adaptive. Cute but not adaptive, right? In contrast, some other animals actually exploited humans, right? Like rats, right? I actually learned that the brown rats also originated from China, spread all over the world with humans. Why? Because, they can digest almost anything. They can live almost anywhere. They can somehow live, can you imagine panda living in New York subway? No, but the rats can, right? So that's their resilience, that's their adaptivity. So, why some species like rats can be highly adaptive? That's what Professor Shane Campbell Staton gonna talk about, what we can learn from them for engineering. Then the next question, of course, is how can we engineer such a system, right? What technologies are available? And roughly speaking, any robots, agents are consisting of two pieces, body and mind, right? Body being hardware, mind being intelligence. So there will be two speakers, Professor Maria Sakowski from Stanford. She's going to talk about, how shape adaptive structures can help future robots to be adaptive in terms of the hardware. And Ethan Yue, he is an AI expert. He's going to talk from the angle of intelligence. But now there's one more remaining question, which is how to design such a system. And of course, there are established space systems engineering approaches, but can we use them for the new RC 3.0? Probably not, because traditionally we use the same process for any space systems, but space system could mean a ComSat around the Earth, or planetary probe landing on Europa, but they are as different as pandas and rats, right? Perhaps the commercial satellite missions are more like business trips. Like, this workshop, you have an hour-by-hour agenda, you know exactly who you're gonna meet, you know exactly what you're gonna discuss about, right? So when you go to business trips, what would you pack in your suitcase? Suit, yes, right? What else? Laptops. What else? Snacks. Oh yeah, there you go. I didn't. Yeah, there you go. But you do not drink toilet paper or something, right? Yeah. So you're gonna bring probably laptops, shirts. The point is that you only bring what you know exactly what you will use them for, right? As opposed to backpack trips. Who have done backpack trips before? Okay, many people. Yeah. Here's California, right? I argue that planetary missions are more like backpack trips. You don't know what's going to happen. You do not have hour-by-hour itinerary. So what you want to bring for backpack trips?
A compass.
A compass. Oh yeah, of course. Yeah, there you go. Right. Water treatments, yes, there you go. You bring something very different, right? Yes. But I just raised two examples. You would probably bring things like Swiss Army knife and ropes. The point is that you don't know, when you pack them, you don't know exactly what you're going to use them for, right? But you're going to bring them anyway because you know that they often come in handy in many situations. So I guess the point here is that, we plan a backpack trip in a very different way than a business trip. I think that's the case for planetary missions. I guess an RC 3.0 mission should be planned, designed, and tested maybe in a very different way than Earth satellite missions. And that's a topic that Alejandro is going to elaborate in his talk. About the systems engineering challenges for designing adaptive one-shot missions. All right, I will stop here and hand over to the 5 amazing speakers. Professor Shane Campbell-Staton unfortunately cannot come in person because, the craze is happening in airspace these days, right? So he's gonna speak through Zoom. All right, so I'm gonna hand it back to, I guess, Harriet.